How's it going? All right, so I have lost my voice and I'm going to do my best here. It's going to be annoying. You might have to turn your volume up a little bit. I'm just going to do my best. We are talking about linear functions, so hopefully this won't be too tough of a lesson. And we can go through it pretty quickly here. So we've been talking about functions in general, but today we're going to focus strictly on linear functions. And when we talk about a linear function, we think of lines in slope-intercept form. So we're used to that y equals mx plus b. This is that format. It's the same thing, just using some different letters, using an f of x instead of a y. The a here just represents the slope. It's just an a instead of an m. This is actually the format your graphing calculator and the letters that your graphing calculator uses. All right, so you can see here that the function f of x equals negative 2x minus 1 is graphed over here. And remember, this is your y-intercept. And the negative 2 is the slope. Think of it over 1. And that'd be your rise and run. So you'd rise a negative 2, run 1. Rise negative 2, run 1. All right, so what do you think your domain and range? That's a review from yesterday. What are your domain and range of this linear function? All right, hopefully you're thinking that your domain is going to be negative infinity to infinity. It goes forever left and forever right, and so does the range. It goes forever down, forever up. So easy little domain and range on linear functions. We're kind of recapping all that stuff that you know about linear functions. So here's another thing. How about finding the intercepts, both the x-intercepts and the y-intercepts? So if you want to find an x-intercepts happen all along the x-axis. And along the x-axis, your y value will always be 0. So if I want to find an x-intercept, I'm just going to plug 0 in for y. And the opposite also holds true. If I want to find a y-intercept, well, on the y-axis, all the x values are 0. So if I want to find a y-intercept, I'll plug 0 in for x. So you're always plugging 0 in for the opposite value. Now, using the intercepts to graph can actually be a very, very quick way to graph when you have a function, maybe, well, different types of functions, but I like to use it when your function is in this standard form rather than this slope-intercept. I'm probably still going to go graph this with my y-intercept and my slope, but when it's in this form, intercepts is oftentimes a better option. All right, but let's practice, even though it's in this form. Can we do our intercepts method? So I'm going to find my x-intercepts by plugging 0 in for y. So if I plug in a 0 right here, I have to solve for x. Now, I didn't leave us much room to do this because I feel like we could probably do this in our head. I'm just going to subtract the 6 and then divide by the 2. So my x-intercept is going to be a negative 3. Now my y-intercept is a little bit easier because for my y-intercept, I'm just going to plug 0 in for x, which is going to make this whole thing go away, and then my y will be equal to 6. So I have a y-intercept of 6. And then with those two intercepts, I can graph my line. All right, let's try this other one. This one is in standard form. It's ax plus by equals c, or your constant. When it's in this form, I like to think of it. Let's see if I have any sort of way to hide these. I don't know. Let's see what I've got here. If I was going to do my x-intercept, I would plug 0 in for y, which would make this whole term go away. And what do you think your x would have to equal then? It'd have to equal 4. So my x-intercept is 4. Now let's try the other thing. To find the y-intercept, I'm going to plug 0 in for x, and this whole term goes away. What do you think the y is going to need to equal? You just divide by the -4. Your y-intercept should be at -2. And then you can draw that line. Now, I like that because it is some quick mental math. Now, that's not always going to be the case. It's not always going to play out that pretty. But if you find that these two coefficients are both factors of your constant, then it's going to be quick and easy, and the intercepts are going to come out as nice integers. Now, if these are not both factors of the constant, then you might end up with some fractions as your intercepts, which is not as ideal. All right, so the next topic is talking about horizontal and vertical lines. These are supposed to be like the easy ones, but invariably because they're special, they don't stick in our mind as well. There's this nice little acronym. I really like this acronym, but it sort of depends on who your teachers have been, on whether you've ever seen this acronym. We just call it HOIVUX, and it's just a way to remember some details about horizontal and vertical lines. So HOI works with the horizontal lines. And what this is saying is that horizontal lines, so I'm going to kind of squeeze this in. So horizontal lines, I'm going to kind of write sideways. Horizontal have 0 slope. That's what that 0 is there. And their equations are always a y equals some number, whatever that might be. But the equations don't have an x in it at all. It's just a y equals a number. All right, so with that, I bet you could help me with VUX then. What do you think the V is going to stand for? Vertical lines. And vertical lines do not have 0 slope. They have undefined slope. And the x means that your equation is going to have x equals some number. There's no y value at all in that equation. So keeping that in mind, let's see if we can graph these. Now, I chose to use some function notation just to get you used to that. But remember, that's really like seeing a y. So this is a y equals -2. Okay, if there's only a y in it, that's going to be HOI. So this is going to be a horizontal line. And the horizontal line is going to happen at -2, because ultimately this is saying all your y values equal -2. So if all my y values are -2, that would happen right here at this horizontal, oops, not there, sorry, down here at -2. Look at your next one. This one is an x equals 3. There is only an x in it. So that's going to be VUX over here. And that means you got your x equals a number. So you have a vertical line. Your vertical line is going to happen at 3 because all of your x values are going to be 3 over. So the vertical line that is 3 over is this one right here. All right, the last example I have for you is this one right here. Do you think this is the HOI or the VUX part of that? I hope you're saying neither, because really this is a y. And what I have here is a y equals an x. So I have a y and an x. That is not HOI. It is not VUX. This is just a different kind of problem or kind of graph. If you think of it like a y equals x, that means your x and your y are always the same. So if my x is 3, so is my y, and it would plot right there. If my x is 5, so is my y, and I would plot that right here. If my x is 0, so is my y. And I could do it all day long. But you can see these are starting to line up. And so this is the nice y equals x line that is a perfect diagonal line right through the origin. All right, so the next topic about linear functions, let's talk about slope. All right, I have a nice little diagram of all the different ways that the slope can play out. This first one, I know this is teeny tiny on your notes, but this, any kind of a line that, remember we talked about increasing and decreasing? If your function, your linear function, is an increasing function like this, then that would have positive slope. Decreasing functions have negative slope. If you happen to have a horizontal line, we already talked about it, that has zero slope, and vertical lines have undefined slope. So that's what it looks like graphically. Let's work with it with some ordered pairs. It says find the slope given 2 points, then determine if the slope is rising, like would have positive slope, would be increasing. Whether it's falling, okay, that's negative slope, or decreasing, if it's horizontal or if it's vertical. All right, now I didn't really put a spot for you to write your slope formula. I'm going to guess you probably know it, but let's go ahead and write it in our notes just in case you don't. So the slope formula, m equals y minus y over x minus x. Make sure you get your y's on top. So on this first example, A, I've always said it doesn't matter which point you start with, you just got to be consistent. So I'm going to start with the 1 because that's a y. I'm going to do 1 minus 0. That's my y minus y over 3 minus negative 2. Right? Change those signs, and it looks like my slope is 1/5. Now, if your slope is 1/5, which one of these scenarios do you think you have going on? All right, I hope you're saying this one. Because you have a positive slope, then this is going to be a rising line. So I'd say it's rising. Okay, next one. Let's see what happens here. I'm going to do y minus y. So something like 2 minus 2. Lots of 2's in this one. 2 minus 2 over 2 minus negative 1. All right, that's going to change to plus plus. And over here, I'm going to have a 0 over 3. All right, I don't really care what this denominator is because I have a 0 on the top. And when I have 0 in my numerator, you can type it in your calculator, 0 divided by 3. It will always be 0 if you have a 0 in the numerator. So you might want to jot up here that when you have, okay, I'm sorry, I'm getting sidetracked. First of all, you have to commit to a 0 or an undefined. If 0 is in the numerator, that is 0 slope. And we said earlier, that's a horizontal line. So this is going to be something like 0 over some number. If you have it the other way around, some number over 0, that's considered undefined, and that would be a vertical line. But my example that I have on B looks like it's going to be a horizontal line. So when they're asking me rising, falling, horizontal, or vertical, since I got a 0 slope, I have a horizontal line. All right, let's take a look at average rate of change. Rate of change is a fancy way of saying find the slope, find the rate of change. Well, that's really what slope is telling you, is how rapidly is it changing. We talked like the very first day of school about something. If something is happening very quickly, then your slope is very steep. If it's happening slowly, then it's sort of a more gradual, less steep of a situation. So let's look at what's happening here. In 2013, Amazon spent $6,565 million on research. So really, you're talking it's about a 6.565 billion on research and development. In 2017, they spent $22 $1,620 million on research and development. All right, so if we're assuming a linear relationship on what their spending is going to be, then I want you to find the average rate of change in the amount of money spent on research and development per year, and then interpret the results. Okay, so ultimately, if they want the average rate of change, I'm just going to go find my rate of change over that time period. It may not have been consistently the same, but we're finding the average. So one year might have been a little high, one year might have been a little low. By going from 2000 to 2013 to 2017, we're finding the average. So look at these as ordered pairs. 2013, 6565. I'm not going to add all the zeros on it. Just know that that's in millions. And then we have a 2017 number, 22,620 million. And now let's do y minus y. So to find the average rate of change, that's just a fancy word for slope. Here I go. Slope is y minus y over x minus x. All right, I know my denominator is going to be a 4, and didn't have my calculator ready, sorry. All right, so then I'm going to do 22620 and subtract the 6565. All right, and I'm left with 16055. Now, it would be nice if that reduced. It doesn't. I could maybe go to a decimal on it. That wouldn't be terrible. So what you do is kind of going to vary on how you interpret this result. If this doesn't reduce nicely, I'm going to go ahead and leave it like it is. We oftentimes wanted to put it over 1, and you could do that as well. But what I'm going to say on this is that remember that these are your y values, and your y's are representing money. These are your x values, and that's your years. And so what this is indicating is that every 4 years, Amazon spends additional and don't forget your million on this, dollars. Okay, maybe you want to change that into billions. It'd be about 16 billion. I'm just going to leave it like it is for now. So when they say kind of write a statement to interpret the result, this is what we're talking about, is this statement right here. Now, on that last example, I wasn't really finding the average rate of change. I found the rate of change. It was only 2 ordered pairs. I found a linear rate of change. The average rate of change is more of something you're going to do when you don't have a linear situation. So you can see on this example, I'm looking at the blue part. It's very shallow. It's a very low line, not very steep. So I know that this is something happening slowly. And then you can see it starts to take off, and now it's getting really steep. So if I were to try to find the rate of change, it wouldn't be consistent on where I'm at. So then what I do is I find the average rate of change. I pick a couple points somewhere on that curve, and I go find the rate of change from one point to the next. So this example here is going to tell me the average rate of change from year 30 to year 47, right there. Okay. Let's read what we're talking about. So the graph shows the annual federal spending for healthcare. Okay, so the spending must have taken off here from 1970 to 2017. This is in billions of dollars, and this is the number of years after 1970. Asked me to find the average rate of change of spending from the year 2000 to 2017. All right, so let's think about this. We're thinking 2000, but remember, this is years after 1970. So 2000 would be 30 years later. So you can see right here, that's why they've given me this point, because that's at year 30. And year 47 would be the same as my 2017. So that's these 2 points representing these 2 years. They want us to go ahead and find it. I suppose let's go ahead and do that. So I'm going to do y minus y. That's going to be a 3612 minus 1329.4 over x minus x, 47 minus 30. I know that's a 17, and I'm going to grab my calculator to do this one. Right? 4982.6. Okay, so what this means is that every 17 years, this is how much it increases by. That's the rate of change, at least in this time frame here. If I were to choose a time frame from here to here, it wouldn't be as dramatic because it's a lot less steep. I don't really love this. I would probably be inclined to go ahead and divide that out at this point. I mean, I already have a decimal. I really don't think it's necessary to have a decimal and a fraction all in the same answer. So when I divided that out, I ended up with a 293.1 is what I'm going to say. And you think of it as over 1. So now what I've managed to do is get this down to break that concept down to each year. The spending went up by 293.1 billions of dollars. All right, we made it to the last slide. Here is a situation where a linear function can be used in an application, and you know we've been doing lots of applications. This one is a new formula for us that we maybe aren't familiar with or haven't used at least this year. But ultimately, it is a profit function. And to figure out how much profit you make, you look at what your revenue is. That word revenue just means money coming in. How much money is coming in? You take all the money that you've made, you subtract out your cost, and you're left with your profit. All right, so it says assume the cost to produce an item is a linear function and all items produced are sold. So we don't have any leftovers, we're selling it all. The fixed cost that we have to operate, this might be like purchasing machinery, or maybe it's buying a building for your shop or whatever that is. Your fixed cost is $1,500. And then the cost to produce each item is $100. So if I'm making a pair of shoes or something, it's going to cost me $100 to make that pair of shoes, that pair. And then I'm going to turn around and I'm going to sell it for $125. We're going to write linear functions to model each one of these scenarios. Now, this is not that tricky of a problem. I purposely chose something kind of basic so that you can kind of understand this process so you're ready when we start throwing a more complicated scenario at you. So don't try to go solve it in your head. What we're practicing is writing functions, linear functions. So I'm going to start off with a revenue function. This is a function, so I'm going to call it R, And it is going to be based on how much money I make, is dependent on how many items I sell. So I don't love an I, so I guess I'm just going to use an X, and X represents how many items I'm selling. So the revenue based on how many items I sell. Now, don't overthink it. Revenue is money coming in. What up here in this information talks about money coming in? All right, it's the 125. It's the only thing that I have money coming in on. So my revenue is simply $125 times X. I get $125 for each item I sell. I'm going to have that much money in my register. Okay, let's talk about cost. This is a cost function. So we write C of X. Now the cost function is money going out. So I'm only thinking about, what am I spending money on? Well, I know that right up front, I have to have $1,500 to buy that machinery or whatever that is. That's a flat fee right up front. But then after that, I still have to make the shoes, and I am also have a cost of $100 per pair of shoes. That is my cost function. And then right here, a profit function, I'm going to write it here. The profit function is always going to be your revenue function minus the cost function. You take the money coming in, subtract the money going out, and you figured out your profit. In this case, my profit function will be, my revenue function is 125x minus my cost function. My cost function is actually a quantity here, so be careful. I'm going to end up having to distribute that minus sign through the parentheses. All right, I didn't give myself much room, so I'm going to work horizontally here. This minus sign is going to distribute. I'm going to combine like terms, so I have 125x minus 100x. So this is going to be my final profit function. 125x minus 100x is 25x, and then minus 1,500. Now, I know in your head you're thinking like, gosh, I could have solved that 10 minutes ago. All right, it's not about solving it. We're trying to set up these functions and get familiar with how to write functions. Okay, then you can sit there and use your profit function to answer questions. It says, how many items must be sold for the company to make a profit? All right, well, if I want to make a profit, then what does that mean for my P of X? Yeah, I feel like this is more of an inequality, because to make a profit, I need the profit here to end up being greater than 0. Okay, so here's how I'm going to set this up. 0. We kind of sometimes will call this like the break-even point. 0, if I make $0 in profit, I just broke even. But I'm trying to make more than that. So I want to have this 25x minus 1,500, my profit function. And I want my profit to be greater than 0, not even an or equal to. If I did an or equal to, I would only break even. I want to make a profit. Let's solve this then for x. Add the 1,500. Divide by 25. That's 60, but I should check this up. I don't want to make a video and then have it be wrong. Yes, 60. All right. Now this might look backwards to you. You could rewrite it the other way if you like. So x is greater than 60. The question was, how many items must be sold for the company to make a profit? I have to make more than 60. If I make 60, I break even. I have to make more than 60 to have a profit. Let's make a statement. Must sell more than 60. And what's your label on the 60? It is not dollars. It's really just items, right? Must sell more than 60 items. All right, there we go. Lots of different stuff, but none of it's too tough, hopefully, for you. Your homework is probably in my math lab. I'm going to turn you loose. Be good.